Welcome to Purdue University College of Science Superheroes of Science podcast. I'm Stephen.
And I'm Sarah. We will be discussing anything and everything related to the science classroom and interviewing scientists.
Because as we know, scientists are the superheroes behind the science.
So join us as we learn about the scientists and explore current trends in K-12 science education. Welcome to Superheroes of Science. We're here today with Chris Andronicos, Associate Professor of Geology in the Department of Earth, Atmospheric, and Planetary Sciences here at Purdue. Welcome, Chris.
Good morning. Thanks for having me.
What got you interested in science is where I want to start with. So, started at a younger age, did young Chris decide, I think this would be cool, I want to do geology? Or when did you start that? What's your background?
So I grew up in northern New Mexico, and so it's quite a bit different than Indiana. Lots of mountains and high mountain desert and things like that. We had winter, but it lasted. It came in spurts of like 2 days at a time, and then it would be really nice in between. And so the long cold of the north is quite a bit different. As far as like how I got interested in things, it was really accidental. So I grew up in northern New Mexico, and there was a lot of science around me because you had Los Alamos National Labs and Sandia Labs and Phillips Labs and things like that, and Honeywell and Intel and all kinds of things like that. And so science and engineering were big things in my childhood, but I had no idea about geology. And growing up where I did, there was lots of mountains and stuff, and I loved to hike and I loved to mountain climb, but it never occurred to me that you could make a career out of studying mountains, right? And so I was about 19 years old working in Albuquerque, New Mexico, when I met my future wife, and she had just graduated from University of New Mexico, and she actually took me to the university and registered me for classes, helped me do that the first time because, she could see that I needed some direction in my life and things like that. And so I started, in the College of Science at New Mexico. I thought I would be a physicist because that's what people did at Los Alamos and things like that. And I had known some geophysicists as a kid, but never really thought about exactly what they did and things like that. And then I took a geology class my sophomore year, and I was like, these guys get paid to go camping and they're scientists. This is the job for me. And so I started studying geology, was very fortunate, had a couple of really tremendous mentors. Jeff Grambling, he was a petrologist, someone who studies the origin of rocks, and another guy, Carl Karlstrom, who's still a big influence on me and a good friend. He was a structural geologist, and I went to work for Jeff and Carl, basically studying how you made the mountains in northern New Mexico, and that's something that I have managed to continue to do for the last, 30 years now. So that's been a pretty good adventure.
So you never completely got out of New Mexico?
Yeah, I still do active research there. I work in a lot of other parts of the world now. I've been fortunate enough to have worked in the Middle East, in the nation of Oman on the Oman ophiolite, and I've worked in Alaska and British Columbia and the Russian Far East and Greece and all kinds of places. And so it's been a pretty good adventure.
How opportunities? Wow, I see Sarah's like, what? How do those opportunities? How do you get to go to Oman to do research?
Well, I 2007, the way I got involved in Oman, it's like many things. I had just taken a new job at Cornell University, and one of my colleagues there, a gentleman by the name of Jason Phipps-Morgan, invited me on a field trip to visit the Oman ophiolite as kind of like a geotourism and talk about like, are there projects that you could get to do there? And the kind of things that I study in geology very much revolve around earthquakes and volcanoes. And Oman is kind of a very special place for that because it's oceanic crust is exposed on land, and that's basically all volcanic. As you can think of the ocean floor as being 100% volcanic in origin. But the way it got there was there's a giant fault, one of the biggest faults I've certainly ever seen, that moved enough so that you put the ocean on top of the continent. And I had thought this will be a great opportunity there because I'm really interested in how you actually do that to be able to emplace the ocean crust on the land surface. And I thought that's what I was going to work on. And I got there and it was like, who cares about the fault, because you actually have about 30 kilometers of the Earth's upper mantle exposed there. And so the Earth's layers, you have a crustal layer and then you have a mantle layer underneath that. And the mantle layer, because it's usually buried by the crust, you never get to see it. You go to Oman and it's exposed for 700 kilometers along strike of the ocean. And it was, I had read about that, but you don't appreciate something like that until you're actually standing there looking at it. And so I started studying the process of how melt is made in the ocean basins that ultimately leads to the formation of oceanic crust at mid-ocean ridges.
So what's melt?
So that's when you heat up a rock hot enough that it literally melts. And you can think of like taking a stick of butter and tossing it in a pan, and you melt that, and it goes from being a solid to a liquid. Rocks do exactly the same thing when you subject them to high enough temperatures inside the earth. And so this was, I hadn't really appreciated that you had this opportunity to study melt generation in the earth with actual rocks that are exposed at the surface in the amount and quality of exposure. A lot of times there's really good rocks that you can see out in nature, but they're small outcrops because we have these terrible things called forests and grasslands and things that cover up the rocks, right? And so Oman, being in the middle of the desert, it suffers from that problem a lot less. And so you have really, really excellent exposure and much more exposure of rocks than you typically have in most places in the world. And then the mountains are very high. They get up to about 3,000 meters, around 10,000 feet in elevation, right next to the coast, and so it's a really spectacular landscape. So I got involved in thinking about how you get melt out of the upper mantle. And that was an entirely new field of research for me because I'd always worked on metamorphic rocks previously, and so I learned a lot about ophiolites and things like that. And it was actually that knowledge that led to me getting to work in Greece. For instance, when I was a professor at Cornell, one of the professors in the classics department asked if he could use my petrographic microscope to look at pottery sherds. And so he brought over some of the fragments of pottery from this Neolithic site he had been working on for a couple of decades. I think he had been excavating at that site. And so I was helping him with the microscope, and I noticed, gee, this pottery's kind of odd. It's full of olivine and pyroxene and things like that. And he said, I said, do you have a geologic map? This is kind of interesting. And he was interested in trying to figure out where the clays came from and stuff. So he brought me a Greek geologic map, and I couldn't read much Greek, but I recognized enough of the letters that I realized, oh, these are ultramafic rocks just like in Oman. And I jokingly told John Coleman, the professor, well, if you ever need somebody to come and make a map on these rocks, I'd love to go. And about 2 months later, he showed up with a plane ticket, and and so I started working in Greece on the Voronis ophiolite, which was the rocks that he had been working on indirectly by studying the archaeological remains that were there. And that was pretty neat because you had basically continuous occupation at that site from the late Neolithic, which I'm going to I'm not going to quote an exact age because I know I'll get that wrong. Because the Neolithic varies in time a little bit, and it's ended a little sooner in Greece than it did in other parts of Europe.
What's Neolithic?
So the end of the Stone Age, basically. And so people had started to build houses and had agriculture and things like that, but they hadn't organized to the point of having government and armies and things like that. And so this community, it was there and started off in the Neolithic, and then you had ruins from the archaic period of Greece, sort of, Homer and the Iliad, and this was actually about maybe 30 kilometers from Thermopylae, where the whole story of the 300 happened and things like that. And then, goes through the classic period and the Roman period, and there was a Byzantine church on the site and all kinds of stuff. But what was neat is that for each different period in history, people utilize the resources different, and so you could actually identify the age of the building by the kind of building stone that they utilized. And then I could go back and look in the landscape and find the quarrying places and stuff, and then you could match the building stone from say an archaic building. They like to use a Jurassic limestone, and we could actually find the quarries where they had quarried the stone to make the buildings, which was pretty neat thing. And so worked on that for a while, and then the way I got into Russia was the same thing. Was my advisor at Princeton knew I'd been working on ultramafic rocks, and he had been involved in a project looking at really novel alloys of copper and aluminum, which weren't supposed to exist, that came from Russia. And part of the story there was the place where the original samples had been found was in an ophiolite complex in the Koryak Mountains, basically opposite Alaska on the northern part of the Kamchatka Peninsula. And so they needed somebody who knew about ultramafic rocks and also was used to camping with bears and stuff, which I had done a lot from working in Canada. And so I was actually
used to camping with bears.
To camping with bears.
Yeah. So I was
prerequisite.
I was coming back from Oman when I got a phone call in the Kennedy airport inviting me to go on this expedition to Russia, and so went off on that expedition, and that was a pretty spectacular story. Got to go to parts of Russia that most Westerners will never see, and all of that, and that's been a pretty good adventure working on these copper aluminum alloys. They are very unusual because minerals that occur in most rocks only have certain geometric properties, and they follow a very specific set of rules for how you can put them together. And it's kind of the way to think about this is atoms in a crystal structure are stacked up in ways that make sense, kind of like the way you would stack bricks up to make a wall, right? You have certain combinations of the ways that you can organize the bricks, but unless you don't care about the wall having holes in it or standing up or things, it's really limited the number of ways you can stack the bricks. And we can predict that mathematically. These copper aluminum alloys, they actually manage to stack the bricks in different ways that violate those rules. And so that was a major discovery in material science that was made in the early 1980s. One of my collaborators, Paul Steinhardt at Princeton University, came up with a theoretical explanation for these materials, and then they were synthesized by Dan Shepman, a material scientist, in 1982, I think, is the timing, and then he won the Nobel Prize in 2012 for having synthesized those materials, Nobel Prize in Chemistry. And it was the spring of 2012 that we had actually gone to Chukotka and recovered some of this material ourselves. And it's the first documented natural occurrence of quasi-crystalline materials. We've actually named about 4 or 5 new minerals that we found on stuff that was recovered during that expedition, and I've got an undergraduate student working on some soils that we collected from there, hoping that they've been gone through before, but I'm having them do it again, hoping that they'll find a few more grains of these things, because they're very exotic materials.
I mean, I didn't think there were any minerals that had not been discovered, identified, and
so 3 of the minerals that we have discovered not only had not been identified before, but had structures that had never been observed in nature before. And it's really quite remarkable what Paul and our group has been doing, and Paul is really the lead on this. I'm lucky that I get to participate in it. But, we're talking about new state of matter with quasi-crystalline materials. They have all kinds of properties that are different than other states of solid matter, and they follow a different set of rules for putting them together. And the really wild thing is they are meteoritic in origin. They did not come from they weren't indigenous from the mountain range. We know that they came out of a common meteorite type called a carbonaceous chondrite now, and we didn't know that when we first collected the samples.
oh, Sarah's still gonna laugh at me, but all right, sci-fi right there, alien material, right? It's there.
Every episode.
It has been. That was actually seriously one of the hypotheses that we had to rule out. Is how do we know this isn't the crashed spaceship stuff? And I don't think any of us really believed it, but if you're really being open-minded with, especially given as odd the combination of metals is, because you should never have an alloy of copper and aluminum in nature. We've made them a long time as people. Different forms of brass, for instance, but to have that combination of elements in nature is really unusual, and then to have that combination of elements in a quasi-crystalline structure is super rare. And so we've gone through a lot. There's been a lot of pushback, people saying, no, you guys made this up, you screwed up, it's contamination, it's every possible thing, it's aliens. And we have pretty much, met the challenge of all the tests and things like that. And now other people have discovered similar materials in other meteorites from other places. And so I think the science is becoming pretty widely accepted. But 2 or 3 years ago, I was like, man, have I got myself into something that's just not going to end well?
Yeah,
you've gone a lot of places.
Because there's so many questions I have.
You've gone a lot of places, and you've got to study a lot of really neat things. What are the types of data or measurements or things that you take when you're out doing field work?
Well, I really am a generalist, and so I have, in my own research, I've used everything from, seismic waves and gravity, sort of traditional geophysics things, to look at really large-scale features of the Earth, whole mountain ranges, all the way down to using transmission electron microscopy to study the materials that we were talking about. And I guess, if I had to pick one tool as being the thing that I'm expert at using and stuff, it would be an optical microscope, just a really simple petrographic microscope like you could find in just about any geology department in the world. And the microscopes themselves are a little expensive when you buy them, a few tens of thousands of dollars, but they have a lifetime of 40 or 50 years, and it only costs about $15 to $30 depending on how you do it to prepare a sample for analysis. And then I can tell you all kinds of things about a rock. And
by using a microscope.
By using just a simple microscope, there's so much that you can learn. And of course, I like other analytical techniques, determining the ages of rocks and all of those things. But if you told me you can only have one thing, I would definitely take the petrographic microscope, because I could tell you all kinds of things about a rock with that very simple instrument that you could figure out other ways, but they would be much more difficult and things. So it's like a basic thing. I am a field geologist, so my ultimate data comes from looking at the rocks in the field, and I use a Brunton compass. It's a really simple device that lets me measure the orientations of certain features in rocks. Then I can compare those features from point to point around the surface of the earth as I walk around and make a map. That often lets you figure out large-scale geometry features that you couldn't figure out otherwise. And tell stories about, like, there was a giant fault in this place that was active, and you collaborate with your geochronology friends and they tell you when and things like that, and then you put together stories about, like, how you made British Columbia or Alaska or southern Colorado or Oman just by looking at rocks, taking strikes and dips, and looking at the thin sections under the microscope. It's you can do many, many much more technical things than what I do a lot of times, but I think a lot of times the simplest, most unambiguous data in geology is also the most resilient and most least uncertainty in terms of being able to put a good story together.
So if you're walking up to, and we call an outcrop is just an exposed, how would you define it?
Exposure of rock that has not moved since it was formed. And so that's an important one, that it hasn't moved. Indiana's problematic for me.
Why?
Because most of the rocks that you find in Indiana have been moved by glacial ice, so they're no longer attached to the core of the earth, as I like to say, and I like the ones that have stayed where they are.
So if we go down, let's say, the southern part of the state,
yep,
and look at the Mitchell Plateau area,
yep,
where we have things that have been there, and we're driving through, and they've blasted part of this rock, the hill, mountain, I guess I would call them mountains, you would call them speed bumps. I'm supposing you have a little bit taller hills than we do in New Mexico. But what's the first thing you're looking at? I see it, people say, oh, those are cool rocks. I see it like, oh, what type of rock type is that? Because I know there's a story behind it. But what do you see when you walk up to that?
It's kind of funny that how that has changed so much for me, because I think when I first started out, I looked at things and I saw color and I saw structure, and I would always be looking for things like what we call bedding planes, which are layers that form in the rock due to their deposition at the surface of the earth and things like that. But I've looked at so many rocks now. I was on short vacation with my wife recently for our 30th anniversary, and she was handing me rocks, and I was telling her what they were before I looked at them, and I realized that you could hand me a rock a lot of times and I can identify it just by touching it. And so
that's like a superpower.
It is, but it's like a really hard thing. I'm teaching mineralogy right now, and the students a lot of times ask me, how do you know it's that rock? And I'm like, well, because it looks like it, and that's the most unsatisfying thing for them, because I'm not telling them all the things that you have to do. And so what I see in rocks is really changed for me tremendously. And a lot of times, rather than just thinking, it's a limestone with a gentle dip to the east, I'm immediately thinking, that's, dipping into the, Illinois Basin on this side, because it's, on the Kankakee Arch or whatever, and that's a high spot and always has been. And so it's like, I kind of know too much now about things to look at them as a normal, healthy human being would.
Well, we're not here to accuse you of being normal. Advice. What advice? The podcast, both teachers, it's like
K-12 students,
teachers, if they're listening to this.
We're going to interviewing people to give them an idea of careers that are out there,
yep.
careers related to science that are out there. And so we're thinking of students sitting and listening to this who maybe aren't quite sure what they want to do. What advice do you have for them as they pursue science and other subjects?
Yep. Well, my wife and I are both the first people in our families to graduate college, and she's actually featured on the College of Engineering website now because they have a website that's first generation people in engineering. And I'm talking about that because the advice that she gives on there is so awesome. It's her quote is something like, persistence is the only valuable thing, or something to that effect. And I would say, and she got it off a fortune cookie. But when I think about both of our lives, it really has been persistence. It's been persistence in, our relationship with each other. It's been persistence with our professional goals. And it's been persistence in, when I graduated high school, I wasn't good at math. When I went to college, I had to take all remedial math and things like that. But I stuck with it, and now I work with numerical modelers who do really advanced techniques, and I give them advice on how to do their models and things like that. And the only way that happened was by persisting and saying, I'm going to keep working on this until I figure it out. And so I think that's the best advice is that I could give anybody is just keep going. If you really want it, you'll get there.
That's excellent.
I like that. That's excellent suggestion right there. Mm-hmm. I know more than once if I hadn't been very persistent, I certainly wouldn't have achieved my goals.
Yeah.
Mm-hmm.
And I didn't know what perseverance was when I was in high school as a term.
Yep.
But I remember a teacher, his metal shop class, the first year I was terrible at. But I took it, and I knew I was terrible, and it was to the point I was in before school every day just trying to grind the right angle on a tool or something for assignments. And then we had to do the welding. My welding was terrible. And he told me, he goes, you're not passing on your skills, but you are passing on your perseverance. And I had no idea what that meant, but I was just happy I was passing.
Yeah. And sometimes that's all you can ask for.
On some of those, it goes, your welds passed the test, but there's no way you're welding on anything I own personally.
Yeah.
He's like, I'm not sure how some of these actually passed. But I did stick with it. And I've found, I agree, that is, to me, one of the most... one of the factors that will lead to success beyond natural skill. Yeah, and
that's something that I think is a really good point that goes to temper persistence and perseverance with the fact that, sometimes good enough is good enough.
Yes, it is.
And people, I think, students especially forget that sometimes when they come to college and they take their first calculus exam or something. And a lot of kids at places like Purdue, they come here and they've never made a bad grade in their life. And then all of a sudden everybody here is just like them, and now you're getting a C. It's like the end of the world. And it's like, no, it's not. That's good enough. You passed.
Yeah.
I do think that's really good to hear, because I think you're exactly right. There are a lot of kids that are almost scared to try anything because they don't want to fail at it, or they see it as a failure.
Yeah.
It might not be a failure.
Yeah.
But yeah, I agree. Sometimes it's good enough.
I just like that you started off with you get paid to go hiking.
I do. It's a great job.
The last question we always ask is, what would you do if you had a weekend with no responsibilities, just for you? And I got a feeling you've answered that as soon as you sat down.
Yeah, pretty much, because I like when we go on vacation, a lot of times I pick out places because I want to go see the geology there. And I'm fortunate that my family tolerates that from me. I try to pick nice places that have good geology.
I like that. As someone who's always been interested in that myself. Well, thank you. We appreciate your time. This has been really cool.
Yeah.
Thank you for listening to our podcast.
If you love Superheroes of Science, be sure to subscribe, rate, and give a review on iTunes or your preferred podcast player. Be sure to join us as we add interviews of scientists and incorporate discussions of current trends in K-12 science.
Until next time, be super, and remember, you are someone's hero. Boiler up.
Hammer down.